So the course kind of let up for a few days there. This week's lab was easy. There was nothing due for a little bit. So that kind of comes to an end here. Genetic algorithm, the description for the assignment is out there. You can get started on this. You should have, after today, everything you need to do this complete assignment. I just finished the document. I'll get the grader up, of course. There are some more details I think I want to add to the description. And I want to talk about the assignment a bit in lecture, which I'll probably do on Monday. But the description is out there. You can take a look. You can get started on this one. The structure is slightly different in that, I've got a lot of you are looking at it already, in that the primary objective is kind of the first thing that you do in this one, and then the remaining three objectives are going to be applying the primary objective. So the primary objective is write the genetic algorithm. So for a quick overview, a genetic algorithm is going to take some loose parameters and an optimization problem to solve, and it's going to basically just keep guessing and checking a bunch of random solutions to try to optimize a solution for that problem without actually having to solve it. So this is kind of a first taste of machine learning. It's a fairly straightforward algorithm as far as machine learning algorithms go. This is one of the, I'm hesitant to say this, but it's one of the easier ones to code and to understand. If you're interested in machine learning, things get a lot deeper, especially when you're training algorithms. But anyway, I'm getting up there. So this genetic algorithm, we need a way for it to make guesses and a way for it to check if a guess is good, like how good is this guess. So this function, this method that you're going to write, is going to take in, most importantly, an incubator function, which is going to take a list of doubles, which we'll call genes to keep in the theme of the genetic algorithm. So your algorithm is going to come up with a random list of doubles, which are going to be the genes, which are going to be used to create an animal or a potential solution to the problem. So you call this incubator function to take a list of genes that we randomly generate and then come up with some solution, something in the solution space. The second parameter in this is a cost function, which takes in a potential solution and gives us some cost of it. So we're going to generate random solutions as lists of doubles and then come up with the solution that we're guessing, throw that into our cost function to figure out how well this solution performs on the problem that we're trying to solve. It's going to give you some double where a 0 is a perfect solution, and then the higher the cost, the worse that solution is, the farther off the market is. So we want to just keep guessing until we get a solution that has a very low cost, and then return the solution that gives us that minimal cost. So that's our goal with the genetic algorithm. I gave a few links, and of course, genetic algorithm, they're pretty well known. You can search around and get a lot of information on these. But I didn't specify exactly how to write your genetic algorithm. That's up to you, how you're going to do your guessing. There are things like mutations and breeding between these genes, and it has a lot of correlation to genetics, to actual evolution and genetic algorithms. That's where a lot of the ideas come from. So you come up with a bunch of random sets of genes or random animals. You see which ones perform best. You take the best out of those and then mutate those best ones, create their offspring, create a bunch of mutations of them by just randomly adding some random variations to each of their doubles in their genes. And then also mate some of them, take 2 of them, and then mix their doubles, their list of doubles together, their genes together, to create all their offspring for the next generation. And then also generate a bunch of random ones, just to make sure you don't get caught in a local maximum or minimum. And then run the next generation. See how they all do with the cost function. Take the best ones and just keep repeating the cycle over and over and over, and you'll slowly get to a pretty good solution for that problem. You'll never get perfect, you'll never get an absolute one, but you'll get close enough for some applications, for a lot of applications. The applications we'll see, the first one, just to test how your genetic algorithm is working, very simple, just guessing a value. So a single double value, run your genetic algorithm, and make sure your genetic algorithm can work to approach this, this minimum, this solution of just finding a number. The next one, we expand that a bit and find a polynomial. So polynomial regression is a fairly tricky question to solve. It takes some linear algebra, some systems of equations and things like that. It's not too crazy, but if we have this tool that can solve these things, that can approximate these solutions for us, we can actually solve something like this without understanding how to do polynomial regression. So the next one, come up with, write your cost function and your incubator function to be able to do polynomial regression on a set of points. So given a set of points, give me a polynomial that best fits those points. Then the last one, we're going to pull in some of our physics and have an aimbot in a 2D space. If I have a stationary, like a sentry or a tower, I was thinking tower defense, and I'll show a tower defense game that we made last semester at some point. And I have a tower and a moving target. How do I aim so that I hit that target? Again, this is something that can be computed, but we can use our genetic algorithm to solve this without going through all the math, we don't have to understand all the physics and stuff. We just have to figure out, okay, if I aim here, what's the cost of that? So how close did I get? If we can answer that question, then we can throw this into our genetic algorithm and have it solve it. And for the brave, the bonus is going to be training a neural network with this genetic algorithm. I wanted to so bad put this in the assignment proper, but it's a bit much, so I had to shove it to the bonus. But training a neural network, it's fun. I already wrote mine up. It works pretty well. It's actually awesome to see it working. But fairly tricky. Not too crazy, but just a little bit too crazy that I didn't put it in the assignment proper. So bonus objective, training a neural network. Super fun. If you're interested in any machine learning or AI, anything like that, you should definitely take a crack at this bonus because I think it's really cool. It's really fun stuff. All right, any questions on that before we get into the next thing? Before we get into some new content? So, and the main goal, the main idea of the genetic algorithm homework is this idea of first order functions. That's really what I'm after on that one. Genetic algorithm is just an application that begs for some first order function usage. Passing this cost function as a parameter and returning it from a method, things like that. So it's the first order functions that we really want to focus on for that assignment. All right, merge, sort, and recursion. Lecture question, it's fairly straightforward. If you know what you're doing, this is a really easy one. But it does ask you to write a method that returns a function. So I want you to get used to that syntax. It's one of the things you have to do on the homework assignment. It's the last piece of the homework assignment that we haven't done in a lecture question in that regard, in terms of what Scala can do, what programming can do, the last concept that we have to do. So just getting you familiar with the syntax of a method that returns a function. So this, it doesn't do too much interesting, admittedly, but we want this method named strange addition, which takes in an int and returns a function that takes an int and returns an int and adds that int that it takes to the input of the method, which is a mouthful. You might have to read this one a few times. I was trying to reword it to make it make the most sense. I gave an example to hopefully clarify. But when we call strange addition, it's going to return a function. So adder here is a function. And when I call this function, it's going to add 5, or whatever this input was. It's going to add 5 to the input here. So I want to add 5 and 3. This is my strange way of doing it with returning a function. All right. Let's get into it. And that'll be, you'll write methods that return your cost functions for the homework. Each objective is set up that you have to return a cost function. So I just want you to get used to that syntax. All right, let's get into it. Let's get into some new content. Some of this is a little bit reviewable. of 115, but I want to go deeper into those topics that we briefly mentioned and showed in one lecture in 115 and said, well, isn't that cool? I want to zoom in a little bit and say, okay, what actually happened here? In today's slides, I might not get through all these. Some of these might get pushed to Monday, but I'll at least get through the sorting example in the merge sort and the big O notation and stuff. Okay, so when we write an algorithm, how do we measure how efficient it is in terms of runtime of it? How do we measure the runtime of that? And in computer science, in especially CC 250 and 331, and a handful of other courses, you're going to measure in terms of its asymptotic runtime. How long does this function take to run, or this algorithm take to run? In the worst case, but also asymptotically, meaning what's the rate of growth of this, the runtime of the function, in terms of its input size. We measure that in basically the number of steps, which are any basic operation that it takes. So add up all of the amount of, roughly the amount of work that the algorithm does in terms of size of the input, and then that's our runtime. So we have some input. If we have an input of size n, which for our sorting problems that we seen last time and today, n is the number of values in the data structure. So we want to sort some data structure. It has n elements. We're going to measure the runtime in terms of n and measure that asymptotically. So as n grows, how does our runtime grow? That's the question we want to ask. That's what we're after. So for example, if we have, and we use big O notation for that, like we saw last time in 115. So big O of n means that the runtime grows linearly with the input size. So every time I add n more, every time I add, say, k more elements, I'm going to have k times some constant additional runtime. I'm going to just grow, the growth function is some linear equation. We saw a selection sort last time. We saw that this was an n squared runtime algorithm. So how do we get that n squared? A very quick runtime analysis is this loop that's highlighted here. We're iterating over all of the indices of the list. And for every indice, we're going to run this loop. Every indice, we're asking, okay, what's the value that should go here? And then putting that value there. So this loop runs n times. We have an input of size n. We're looking at every single index. This loop runs n times, or O of n times. We have O of n runtime here. We're going to ignore all the constants and everything here in asymptotics, so O of n, linear runtime here. The inner loop, this runs inside of that loop that runs n times, and this loop itself can run in the worst case n times. So if we're, for example, if I is 0 when we're looking at the first index, this loop has to find the min of the entire list. So it's going to have linear runtime. In the worst case, it has O of n. It has n, which is O of n. So we have O of n runtime for this loop as well. Since this loop runs for every single iteration of this loop, we have O of n runtime running O of n times, so we end up with an overall n squared runtime. We have an O of n loop. Inside that loop, we run an O of n loop. That loop, inner loop, is going to run O of n squared times, so we do O of n squared, total amount of work asymptotically. Technically, we'll talk about this more next week. Technically, this specific implementation of selection sort is O of n cubed because I have the stop by method here, which takes O of n time. So technically, what you see on screen is O of n cubed, but the algorithm itself, selection sort, can be implemented in O of n squared if we're not being sloppy like I am here. But again, I want to do that to motivate next week's concepts. We're going to look at linked lists, and we're going to see why this is O of n time. But the algorithm itself of selection sort is n squared. So we want to focus on the algorithm, not the implementation right now. So you might have noticed I took a little shortcut in my abridged analysis there. I said that inner loop runs O of n times worst case, so it's O of n, so we're O of n squared. Well, you might say, well, yeah, but if we're halfway through the list, it's going to run n over 2 times. If we're near the end, it's only going to run a couple of times. We're not going to get that full n in that inner loop. We actually have n for the first index, n minus 1 for the second one, and this summation all the way down to 1, that last index. We just had to do actually no checks, but that second to last one we had to do 1 check and maybe a swap. But this summation is going to give us n squared over 2 plus n over 2. And in asymptotics, we're going to only look at the highest order term, and we're going to ignore any constant factors. So we still end up with an O of n squared asymptotic runtime. Even though it's not strictly n squared runtime, it is of order n squared. We have a degree 2 polynomial as the runtime, so we're going to say n squared. That's the runtime. Any questions on that one? Yep.
So just always, when you're calculating the runtime, just go for the largest possible runtime?
Yeah, you're always looking at the worst case input. Yeah, you're always looking at the largest possible runtime. But you do have to be careful sometimes. Like, for example, if this loop, instead of going n minus 1, n minus 2, if it was like n over 2, n over 4, then we can't just say, well, that's a linear runtime loop. And a lot of that stuff, you'll get healthy doses of it in 250 and 331. So you will have to worry about those types of things in later classes. We're not going to stress it too much in this class. I'm not going to ask you to do any runtime analysis on any assignments. I'm not going to ask you to do that, so you don't have to worry about those cases this semester. But you will. You're not off the hook for it. You will in the future. The semester's more about getting that foundation. All right, so merge sort, we mentioned last time that it's an O of n log n algorithm. What does that mean, and how did we arrive at that? So merge sort, quick refresher, and we'll look at this in depth in the next bunch of slides here. But merge sort, the high-level overview of the algorithm is a recursive algorithm that says if the input list has less than 2 elements, just return it. It either has 1 or 0 elements at that point, and you cannot possibly have an empty list or a list of 1 element that's not already sorted, so just return it. The size is less than 2, return it. If the size is 2 or greater, we're going to split the list in half into as equal as we can halves. Obviously, if it's odd, we have to put that extra element in one of the 2 halves. And then call merge sort on both halves. So we're going to say, okay, we can't quite solve this, so we're just going to reduce the input size and call ourself. Merge sort just calls itself on the lower list, and as it keeps repeating this step, it's going to keep making recursive calls until it calls itself on a list of input size, a list of size 1, and those are already sorted. So if we keep dividing this down, we're going to get lists of size 1, and then we can just return them and say all of our lists are sorted. Pretty easy, huh? We can't sort something, so we're just going to break it down and get it to something that's already sorted, and then just return it. And then the last piece of this is when we have 2 returned lists, so at the very bottom of the recursion we have 2 lists of size 1 that are already sorted, we're going to merge them together into 1 sorted list. So we're going to, we call this approach divide and conquer. We're going to divide this into smaller pieces and then conquer by building it back up, building it back into 1 large solution of the original list. So if we have some input list, we're going to call merge sort on the original list. That list has more than 1 element. So we're going to call merge sort on each half, and I conveniently chose a power of 2 here as the size. We're going to split it in half and call merge sort on each half. Each of these halves have size greater than 1. Call merge sort on each half. These are all size greater than 1. Call merge sort on each half. And now we've successfully broken the problem into 8 lists that are all already sorted. So go us, we have 8 sorted lists. Now the trick comes when we have to merge these back together. So we have these 8 sorted lists, and we want to be able to merge them back into our larger list. So we're going to start with our 51 and 1, merge these together, and we'll look in more detail of how we do the merging in a bit. but we're going to merge the 1 and the 51 together. So we know we got to put the 1 first and then the 51. Merge these together, merge these two together, merge these two together. Now we have lists of size 2. We want to merge these together. We're going to merge, we're going to put the 1, the 19, 51, 100, and same thing over here. Merge these together and get back to our full list, and now it's completely sorted. So, like I said, we'll look at in depth of what the merge algorithm, how merge actually is computed, and how we do that efficiently in a bit. But let's take a look at what we just did first. We have 2 recursive calls. And of course, maybe I didn't make that as explicit, but we're talking about recursion today. So I mentioned last time merge sort. As professors, we love merge sort because it motivates a lot of topics. It uses a lot of topics, but in a kind of intro level. So merge sort today, we're going to use it to motivate sorting, or sorry, not sorting, recursion. In 250, it'll be used to motivate runtime analysis. And in 331, we'll use it again to talk about proofs, proving why merge sort is correct. So you'll see it a few times. We like doing that because you know what merge sort is each time you see it. We just want to talk about the new topic using something you already know. Anyway, today it's recursion. So we made these 2 recursive calls to the algorithm itself. So we have a method called merge sort, and we're actually calling itself. Whenever a method or function calls itself, that's where we get recursion. This is one of those topics that looks very strange at first. How is this thing calling itself? It's crazy. What we're going to see, hopefully, it takes a while to sink in, to really understand recursion, to be able to write recursive functions and methods. But let's talk about it. But first, the runtime. I'll give a very brief, like 250, this is their job, that's Andy's job to tell you exactly how this runtime analysis works. But I just want to do a very quick overview for the curious. Each level of this recursion, if we think of it as that tree that I broke down like that, each level is going to have 2 to the I lists of size n over 2 to the I at level I. So when I is 0 at the very first input, we have a list, we have 1 list of size n. Once we go down 1 layer and I is 1, we have 2 lists of size 2, then 4 lists of size, 2 lists of size n over 2, 4 lists of size n over 4, 8 lists of size n over 8, and so on and so forth until we get down to the bottom of the recursion. So we want to know when the recursion ends. The recursion ends when n over 2 to the I is equal to 1. That's when we reach our base case. That's going to happen when I, the level of the recursion, is equal to log of n. So we have log of n depth. We're cutting this in half each time. It's going to take us log n levels to get down to our base case. So our whole recursion tree has log n levels to it. Each one of those levels, we want them to have O of n work. If we have n work at each level total, we're going to get our n log n runtime. So if each level has O of n work, which we need for that, what we need to do to get that at log O of n work, linear work, is we have to write merge in a way that's going to have linear runtime in terms of the inputs. So the total size of each layer is going to be 2 to the I times n over 2 to the I, which is just n. So if the total work across all the calls to merge is linear in terms of the size of its input, then the total work for 1 full layer of the recursion is going to be O of n in terms of the original n. So if we can merge in linear time, we get our n log n runtime, which we better be able to get because I told you it's going to be an n log n runtime algorithm. So that's our quick and dirty runtime analysis. You'll see more in-depth analysis in 250. So to write merge in linear time, we're going to take advantage of the fact that both lists are already sorted. We need that fact. Without that fact, we're just left with a standard merge problem, and we're trying to, a standard sorting problem, and we're asked to sort in linear time. Well, if we already had a method to sort in linear time, we wouldn't be talking about merge sort, we'd just be using that sorting method to sort in linear time. So we have to take advantage of the structure, the fact that we're merging two lists that are already sorted. And in fact, we can't sort in linear time. Can't happen. We can't do comparison sort, any sorting method that takes a comparator that compares two values. Can't be done in less than n log n time. It's proven, can't be done. So we're going to take advantage of that fact, and we're going to, I don't want to read I just want to get to the picture here. And we're going to do that by initializing a pointer for each list that points to the first element in each list, compares those elements, and whatever one is less than, whatever is whatever one comes first according to the comparator that we're using, I'll say it that way, is going to be copied to the output. So here I'm looking at, if I have these two lists that I need to merge, I'm looking at 1 and 2, and assume ints and less than is our comparator. I'm going to put 1 in our output, and then advance that pointer, and now I never have to look at that value 1 ever again. I'm going to advance the pointer and never look back. I'm comparing 19 and 2, copy 2, 19 and 3, copy 3, 19 and 4, copy 4, 19 and 8, copy 8, and once we reach the end of either one of the lists, we're just going to copy all of the contents of the remaining lists into the output. Now, each time we made a comparison there, we're figuring out exactly one element of the output list, and then never looking at that element in the input list again. So every comparison we did, we made progress on the output by 1. So one comparison, one value on the output, sounds linear to me. We have a linear way to merge these lists, and we get our overall n log n runtime. And we know that, so just a little bit more analysis here. If we're comparing 19 and 3, and I know 3 is less than 19, I know everything after 19 is greater than or equal to 19 in this list, so I don't have to compare 3 to anything else in this list. If 3 is less than what I'm currently pointing at, I know that 3 is the next element. We're not going to find anything that's less than 3 in the other list. We're not going to find anything that's less than 3 in this list because it's already sorted. Not find anything less than 19 in this list because it's already sorted, and 3 is less than 19. So I know 3 is my next element. No questions, no doubt that that's the next element. And I can advance that pointer, never look at 3 again, and keep going on with my comparisons. So we have a linear algorithm to be able to merge two sorted lists. To do that, we used our comparator. In my example, I just used the standard less than for the comparator. Is this int less than this int? If it is, the less one, the smaller one goes to the output. So we get that increasing sorted order, the standard sorting order that we would think about. But we're going to use a comparator here. So when we do merge, we initialize our pointers to the beginning of each of our inputs, each of our lists. We have a comparator to be able to tell how they're going to be compared, and we have our output list here. We're going to check, as long as neither pointer is at the end of its list, we're going to compare what the 2 pointers point to, and whatever one is the less than, or breaking ties arbitrarily if the comparator, the comparator will break the ties arbitrarily in this case. But the comparator is going to break ties arbitrarily. But whatever one is less than or comes before according to the comparator, we're going to append that to the sorted list and advance that pointer. Once we get to the end of either list, we're going to check which list we're at the end of and just copy the rest of the contents over to the sorted list that we're going to output. Then output that sorted list. So same thing we saw on the previous slide, just in code instead of pictures, and highlighting, of course, this comparator that we're using. We want to focus on taking functions as parameters. That's one of the big topics, big concepts that we're talking about here. So we took this comparator, just like we did with insertion sort, took this comparator and used that comparator to ask how this is going to be ordered. So just like selection sort or insertion sort, we're just using this comparator to be able to figure out how to sort. So this is another example of a comparison sort algorithm. All right, one last sorting example, then I'll go to the code. I don't know if we'll get through that recursion example, but we'll go to the code and I want to show some examples of sorting in the code. So we saw a few different ways to sort. I said there's no limit to what you can sort in all kinds of crazy orders. And in the genetic algorithm, by the way, you have all these sets of genes. You want to create potential solutions and something. You have to sort those by the cost function at some point. So you do have to use this sorting at some point for that homework. So we can sort by a lot of different ways, but what if we want to sort based on some other data that's available to us? The comparators that we write only take two instances of the type that we're sorting and returns a Boolean. Well, what if I want some third value that I need in my comparisons, and that third value is not a fixed value? It's not something I can hard code. It's something that I'm not going to know until runtime, and it's going to change each time that I run. So for example, I have I want to sort a set of points based on their distance to some reference point. So I have some point, say it's a game, and I have a player position, and I want to sort all of the objects in the game according to their distance from the player, so I can figure out what's close to the player, and then maybe outside of a certain range, I ignore those things or something like that. Say I want to have some reference point where I'm sorting by. How do I do this? And each time I sort, that reference point may change, that point may be moving around quite a bit. How do I write this? If I can only write a comparator that takes two things, and no using global state, that's usually cheating. Don't use global state, it's something I don't harp on much, but it's a bad idea. Where you have global variables, you can do this in like JavaScript and Python pretty easily. You can kind of do it in Scala as well. It's a bad idea to get using those. But anyway, how do we do this? So let's see an example. So this is where we're going to write a method that returns a function. So similar to your score functions in genetic algorithm. The cost function in genetic algorithm only takes one potential solution and returns its score. But for example, for polynomial regression, you would like to take in a potential solution, which is going to be a polynomial, and also the set of points that you're trying to fit. If you're only taking in the polynomial, how the hell do you match it to a specific set of points? That's the problem we're facing there. The problem we're facing here is, how do I get that reference point in this comparator? And the answer is to take in the reference point, in a method in this case, take in the reference point, and bake that reference point right into our comparator function, and then return that function that was built around that specific reference point. So I'm taking in a reference point, and I'm returning a function that takes two physics vectors here and compares their distances to that reference point. And then I'm going to return that as a function, and that's what I'll use in the comparator for my sort. This is kind of the last step in the, at least for this course, in the first order functions progression. So we stored them in variables, we took them in as parameters to methods, and now we're returning them as values. We're returning them from a method, returning a function from a method. So this is like that last piece in that trifecta that we're seeing. And the next 2 weeks is mostly digesting those while seeing applications in data structures. So I wrote a method, takes in a physics vector, and returns a function that takes two physics vectors and returns a Boolean. So now when I want to sort, I'm going to call whatever sorting method I want. I'll use my built merge sort here, but I could just use dot sort with and give it a comparator. Use the built-in, which I recommend when you're actually doing things, but I want to show how the merge sort works. Merge sort are points. Call the distance comparator method with the reference point that we want to sort the distance to that reference point by. Call this method with that reference point, which returns our comparator function that we want to use. So this will resolve to the comparator function that we're going to use for sort. I just want to quickly show one example. This is all mostly at least code that we've seen in the slides, but I just want to run a few things here. I'm going to run selection sort, and I'm going to generate a random list of 2,000 elements. And our first example, the yield keyword. We don't really need to explain that right now, but I'm just going to time how long selection sort takes to sort 2,000 elements, 2,000 random elements. And if we look, it took about 6 seconds. I had time to talk while it was running and everything. It took a decent amount of time for 2,000. Granted, this is my n cubed implementation, not n to the fourth like I thought last time, but n cubed, we're doing pretty bad here. But even if I got rid of that cube factor and got down to n squared, it's still not going to be great. But if we go over to merge sort, I want to do the same thing, just coming up with random values, 2,000 random values. Run this. Instead of 6.2 seconds, I'm down to 0.068 seconds, 63 milliseconds. Then, of course, the question, well, how much can we do here? Let's try 200,000 elements. I want to sort 200,000 elements with merge sort. Less than half a second still. So merge sort, it's a more complicated algorithm. There's a lot more code involved, some more analysis, some more work on our ends to do. But once we implement this more complicated, bigger algorithm, it's actually a lot faster than the simple, let's just keep finding the min and put it in the index where it belongs. We get a lot more performance out of this thing.
What does the yield keyword do?
I'll give a brief explanation, but I don't really have time to go in depth on it. Yield, I guess I can. So we're going to run this loop. The underscore, that just means I'm not using that variable. I can name this variable, it just doesn't matter. Yield is going to run the body of this loop, and I can change this to the syntax that we're used to there. It's going to run the body of that loop, and every time it runs the body of the loop, it'll take whatever the loop body resolves to, whatever value is the last statement in the loop, and add that to a data structure. So I'm creating a data structure with a loop and just cutting down my lines of code a little bit, just having a little bit more compact syntax. So give me n random elements ranging from negative 0.5 to 0.5. Those all go into a data structure. Then I'm going to convert that data structure to a list and store it in my list of doubles here. So I'm just getting n random values and putting them in a list. And we might as well go to 2 million here. So so there might be a misconception, I've merged sort, I'm writing so much more code, so it's going to take the machine a lot longer to run that code, is absolutely false. Even at 2 million elements, we're still only halfway to where selection sort was taking to sort 2,000 elements. So we have a huge difference in efficiency. Part of that, you might say, part of that's because my other algorithm is pretty sloppy. Well, my merge sort's pretty sloppy too. I think I have an extra factor in that one as well that shouldn't be there. I'm in the wrong one. Oh, no, I don't. Wait, let me chase this just a little bit here. Yeah, because I'm running foreshadow merge. I didn't talk about this one this time. But if I run the merge from the slides, We'll go to 20,000. My merge from the slides has a lot of inefficiency in it as well. I think I get an n squared log n with my implementation here. Yeah, at 20,000, we're going pretty slow. So 10 times more elements than, the point is the same here. Let's go down to 2,000 for a fair comparison. It's still a lot more efficient, but I am being sloppy with both of my implementations. But I have this foreshadow merge. I better talk about it since I'm already in here, come this far. So with foreshadow merge, foreshadowing next week's topic, linked list, I'm getting rid of those inefficiencies and actually having an optimized, at least asymptotically optimized merge algorithm that is going to get that linear runtime without being sloppy with how I'm using my linked lists. So if you're interested, look through this and you can see how I'm avoiding moving through that list on every single call to apply, and how I'm not creating a new linked list every single time I add an element to the end, every time I append an element. Topics for next week. I want to try to at least attempt this, getting through this recursion example. Now we saw this an example, I think this exact example earlier in the semester when we were talking about stack frames. I just want to revisit this and kind of refresh our memory on these stack frames and talk about it in this context of recursion a little more. So I used that recursion example earlier in the semester when we were talking about stack and heap, but I really didn't highlight the fact that it was a recursive example. I was just going through the stack frames. So let's talk about this in the lens of recursion and try to understand our recursion a bit more. So when we got to the middle of this thing, now I'll jump, I ain't gonna go through the whole thing again. Let's jump to the middle of this. And when we had all these frames on the stack, we could see how all these recursive calls to the same method were all on the stack at the same time with the same variable names, but on different stacks, on different frames on the stack. So if I'm at this call of compute geometric sum where n was 1 from the input, and I'm going to call this again with n equals 0, we can start analyzing what happens at the base case of this recursion. So when I call that the last time, and one of the details I didn't show last time is each stack frame stores a pointer. It remembers exactly where it was when it started the next frame. So each one of these are right in the middle of line 3. They're waiting for compute geometric sum to resolve so they can continue what they're doing. When n is 0, we get to that base case of the recursion, and if your recursion does not have a base case, that's when you get the stack overflow errors. You're going to keep making recursive calls, putting more frames on the stack, and you're going to fill up all of your stack space. So when we get to our base case, which we better be doing, we're going to get to the end of that base case of the recursive call where we can finally start returning values. We're going to return this value 0. This frame is going to return 0. We're going to the previous frame, remembering where we were. We were waiting for compute geometric sum to resolve. And now that's resolved, we can go populate result with that value in this frame, get our result to the value of the return value of this recursive call, and resume execution going to the next line. Now we're going to return result. We've reached the last statement of our method, so we're returning that value. Return result, we're going to return 1 up to this frame. Compute geometric sum resolve to 1. We'll store that in result. And keep going. So this one is going to add that to its value of n, or its result and its value of n. N was 2, result was 1. So we're going to return 3 to this frame where n is 3. We're going to add that 3 to the returned 3 in result. And then after all those resolve, we're going back to the main frame. After all of those calls resolve, chase through all that recursion, we're going to be returning 6 back to the main frame. And main was waiting for this call right here. It's going to return and then print out that result of 6. So when you're looking at recursive methods and functions, trying to chase through what they're doing, one thing I highly recommend is going through the debugger. It's something I always mean to mention a lot more than I do, but go through the debugger in IntelliJ, run through that and actually look at the stack frames and see how all these things are being called. Do that for merge sort, and if you're having trouble understanding merge sort, just set a breakpoint and step through that function and step through all the recursive calls. It can really open your eyes to actually see how the recursive calls are working on there. So I just want to crack this one back open and show you the recursive calls again. And we're back to the lecture question. I guess that didn't take as long as I thought. Any questions on this? All right, have a good weekend.